All right. Hi, everyone. Thanks for coming to my talk. Michael, I'm a co-founder of Brevis. And before I talk about Pico, let me just kind of give a quick introduction of what is Brevis. Brevis is a smart off-chain verifiable computing platform that allows you to scale blockchain to an infinite level. And today, I'm going to talk about Pico, which is one of our products that is recently released, which is a modular and performant zkVM. So, before I talk about the zkVM itself, let me give a quick introduction about why we are building Brevis. We all know blockchains today are world computers. However, there is often ignored reality. Even with layer 2 scaling and everything, the blockchains themselves cannot run faster than a single server. If you pick any single blockchain, even for layer 2 blockchains, they cannot simply run faster than a single server. What does that mean then? Let me give you a very, very concrete example of that limitation. Right? So if you think about it, on every centralized exchanges, there's always this very useful feature called VIP trader program. The concept is very simple. If you trade it a lot in this month, for the next month you will get a trading fee discount. Every centralized exchange has that. Now, if you think about it, across all the DEXs, Uniswap, PancakeSwap, QuickSwap, you name it, none of these DEXs has that feature. Well, why is that? Turns out that even computing historical blockchain on-chain state and data on blockchain directly is proven to be an extremely hard to do task and an extremely computational heavy task that you cannot do even on layer 2 blockchains. So that brings us to a big realization. That is, if we want to actually match the user experience and match the kind of things you can do in Web 2 to your Web 3 equivalent, you really need a new paradigm of computing. And that is off-chain verifiable computing. So in off-chain verifiable computing, we treat the blockchain not as the main venue of computation, but actually just a glue point of the application. Now, the blockchain themselves can offload very complex and data-heavy computation to an off-chain environment. And in this case, it will be Brevis. And in Brevis, two things happen. One, you will, of course, compute the computation result. But if you just compute this off-chain in a server and stuff it back to the blockchain, the biggest problem is that you lose the trust-free nature of the blockchain application itself. So what do? Well, we generate something called a ZK proof that is attesting to the correctness of the computation result. And then you take both of these things and submit this back to the blockchain. It is the nature of the ZK proof that the verification of the ZK proof itself is so much simpler than the computation itself. No matter how complex the computation is, you can always just verify a very succinct and very easy to verify proof and consume the result directly. The end result is that the blockchain actually offloaded some very complex computation, get the result, and can verify it as if the computation it has been done on the blockchain directly. So, what did we do with this? Well, the first kind of application, the product we built is something called a ZK coprocessor. It focuses on a very, very specific kind of a computation, which is on-chain historical data access and computation. So basically, you can allow a smart contract to see in the past and understand what a user's behavior is by looking at what is a trading event, what is a user's liquidation, what is a user behavior, user balance, and all of these, and use these kind of insight directly in your smart contract. So for that, we work with some of the biggest DeFi protocols in the world, such as PancakeSwap, Euromoney, QuickSwap, and many others to build something called intelligent DeFi. So you can basically dynamically change a trading fee, for example, based on users' ZK proof of their interaction and of their trading volume on these DEX venues. You can also generate trust-free proof of your interaction, of your holding of a certain stable token asset, and start to receive revenue from these underlying stable tokens, like what we are doing with Euro, and that is just announced today. So this really showed us the powerful nature and the powerful use cases of off-chain verifiable computing, because now there are actual real use cases that is facing end user, not just like some infrastructure stuff, but actually matters for the user that are using this. But there's also this very big question of like verifiable computing beyond just the zk coprocessors. Because for zk coprocessor, you don't need to write any circuit anymore, but you still need to write specialized zk SDK code. So how do you handle more complex business logic? And things like real-time Ethereum proving to enable exciting things like a more flexible interoperability and native rollup, and things like verifiable AI inference, that you can actually verify and attest to a model's quality when you receive any inference result out of a black box AI model. So we also need to generalize the support to make more generalized zk computing possible. This is why we introduced the second product for Brevis, which is the Pico zkVM. The zkVM itself is highly flexible and easy to development with some performance overhead. But the challenges with the uncovered when building the zkVM is that for zkVM, for zk coprocessor, there's long developer time when developer more complex logics, and it's very unable to balance between developer time, security, cost, and performance. And there's no very adaptive ways towards fast evolving zk theory. So, when we build zkVM, the Pico, we ask ourselves, what is a good solution here? So we define a good zkVM to have 3 properties. The first and the most important one is actually flexible and future-proof. And the second is performant, and third is development-friendly. Let me kind of expand on that. So when we talk about the future-proof and flexible, we want to have a modular architecture that can allow a zkVM to have interchangeable proving backend. Because the underlying zk theory and zk system have been evolving so fast that we need to quickly incorporate new things into our system. And we also need to have a customizable proving workflow so that applications themselves can choose what kind of things they want. Like for example, not all zk applications wants to be on-chain verified. So for things like self-sovereignty identity or identity-based applications, they don't actually need to have the final step of the on-chain verification performed. And of course, the most important thing here is actually we need to offer a very performant zkVM that is able to offload a very heavy computation to function-level zk coprocessors, which is commonly known as precompiles, but also introduce something new that is app-level coprocessors. Finally, of course, we need to be developer-friendly when they're writing applications with a plain Rust interface with no knowledge of zk circuit needed. So Pico here is really designed to be extremely flexible in improving backend. We are the world's first one that support various different kind of proving backends, including Stark on CollaBear, Stark on BabyBear, Circle Snark on M31 field, and so on. All you need to do here is to really just like change the line of the configuration file, and you can run the entire zkVM using completely different proving backend. And the second benefit of Pico is that it is really designed to be highly customizable. The entire proving pipeline is tunable, and you can kind of switch and combine different things together to even build new kinds of VM out of the current instructions we already have. Now, what this means is that for certain kind of application use cases, such as verifiable in AI inference, let's say you're just trying to verify whether an AI model's output is actually from a known high-quality AI model instead of someone just like gave you a random junk output. Well, in that case, you don't actually need to have the final EVM step to recursively verify your proof into a constant site. So Pico right now is the fastest zkVM running on CPU. We benchmark this on a very standard benchmark machine, and as you can see on various different workloads, from micro benchmark to like Fibonacci, to verifying larger workload such as the Ethereum block execution, Pico has been consistently outperforming other existing zkVM solutions. The important question to ask is that, okay, so you have this GPU benchmark, but you cannot really run zkVM on CPU because it's not going to be economically feasible. So what about GPU? Well, we don't have a GPU version yet, but we do believe that with all the innovations that is underlying the Pico's architecture and modular architecture, these kind of a performance benchmark you're seeing on CPU can be easily translated and even amplified in the GPU land. So we are very confident in the next month or so, we'll be releasing something that can actually generate real-time Ethereum execution proving on a single server. So final thing I really want to stress here is that Pico really pushes the modularity to a new level. For the for zkVMs, all the zkVMs really start to adopt a glue and coprocessor architecture. What that means is that you have a standard RISC-V instruction set to start, and for some very specific computations like SHA, like signature verification, you build function-level precompiles to accelerate them. These function-level precompiles are essentially specialized circuits that you plug into your zkVM. But what Pico does here differently is that we extend the concept of coprocessor all the way up to the app level. So what we mean by that is to essentially integrate with our on-chain data coprocessor. So what that means is that you can now access historical on-chain data in your smart contract by just calling a bunch of specialized functions in the VM to say, okay, this is the transaction data I want to access, and then you have the data available in your VM directly. Now instead of asking developer to write specialized SDK code to build their business logic, we now allow developers to actually operate on these data using high-level Rust code. So you can now just write Rust code to say, okay, now I want to compute what is the trading volume for this user by just writing a bunch of Rust functions. Now I want to compute what is a user's liquidation ratio, what is market volatility, and all these on-chain data can be computed in the Rust land, in a very kind of efficient way. So this actually not only accelerates the developer building time, but also make the entire architecture much more performant, because the our data zk coprocessor is not only just a set of specialized circuit, but it is actually a very specialized system that is running in parallel computing and highly efficiently organized. So not only we have the data access coprocessor, but we also have something called SPA-ZK, which allows you to, we initially proposed this as a specialized GKR optimizer to generate a verifiable inference result for machine learning models. And we're going to release very soon a new architecture to essentially allow you to plug in certain machine learning models using very commonly used machine learning tools into the Pico construct, so you can actually interact with all these machine learning models very efficiently by kind of incorporating our app-level coprocessor in the ZK land. So the benefit of this app-level coprocessor is very apparent. For example, with our enshrined data access coprocessor, when you're trying to prove a trading volume of, let's say, 4,000 trade on Uniswap, using our ZK coprocessor, you get about 32 times performance boost, and at 2/3 of the cost, comparing to vanilla Pico, even though the vanilla Pico version is fast enough. So today I'm just quickly introducing Pico, our newest addition to our product line. But overall, for Brevis, we are trying to build a off-chain verifiable computing future. to not only serve as a way to scale blockchain, but also as a way to generate verifiable computing for very critical, mission-critical applications, such as decentralized artificial intelligence inference, and also identity use cases. With that, thank you all.